And now for your worst case scenario. In section 4.3, you have this very long polynomial with 4 or 5 terms, and the very detailed instructions are solve, right? And so when we want to solve an equation or a function or whatever you want to call it, a polynomial, when it is a polynomial whose degree is higher than 1, so it's not linear, the method of attack will always be the same. You factor it and then set each piece equal to 0. And you hope that it factors nicely, and you hope that they are nice numbers. And we're going to use a ton of different theorems, right? So we know from our leading coefficient rule that I have a 4th degree. So my end behavior will both be heading up, so it kind of looks like a W. And I know that I will have at most 4 solutions where I'm going to cross the x-axis. These guys could be 4 nice, neat, real rational solutions. So the rational root theorem would give us this list of numbers that could be solutions in fact, they actually all are nice real numbers. And we figure those out by taking factors of the last term, so 1 and 6 and 2 and 3, and factors of the first term, good news, you only got 1 and 1. And you take each factor of the constant and divide it by each factor of the leading coefficient. And so the good news is here, our list of possible real roots or rational roots would be 1, 6, 2, and 3, all positive or negative. So I got 8 possible solutions. So anywhere that this guy crosses the x-axis, it has to be one of these 8 numbers. That's what the rational root theorem says. Without a calculator, you would pick your favorite number and synthetically divide and really hope that your remainder is 0, because then the remainder theorem says, hey, if this is a 0, then what you have just found is a solution. And if you found a solution, you found a factor. And that factor theorem helps us then factor the rest of the polynomial. But we're not going to synthetically divide randomly. We're going to go to our handy calculator and type in our polynomial and hit graph, and there he is, and I can see I have nice 2 little solutions here. But there has to be 4, right? And we know because of the multiplicity rule that these have to be odd multiplicities. So maybe it's a 3 and a 1, maybe. It can't be 2 and 2, because then that would be a tag. So we got to figure out what's going on here. So we're going to pick our favorite number, which is probably this one, and I'm going to make sure that that is actually a positive 2 by going into the table and saying 2, 0. All right, so 2 is my winner. I'm going to take 2, put them in the box. Then I'm going to line up my coefficients, and I have no skips, so I don't have to worry about putting in zeros. And I'm going to synthetically divide. Drop the first number, take the number in the box, multiply by the number underneath, put the product in the next spot over, add down. And so we'll do this, and lo and behold, yay, factor theorem, right? This remainder is a 0. That means x equals 2 is a solution. No kidding, we knew that. More importantly, it means x minus 2 is a factor. And just like when you were dividing, real numbers, like real numbers, like 6 divided by 2, you took your quotient and you multiplied it by the divisor and you got the dividend, right? 3 times 2 is 6. Same thing here. My divisor times my quotient, which is this guy down here, will get me back to the function up there. So a semi-factored form of my function would be x minus 2 times, and this is my remainder, this is my constant, this is the x coefficient, x squared, and x cubed. So x cubed plus x squared plus x plus 3. Okay. Now I look at this leftover piece and I say, can I factor you? And no, I don't know how to factor that thing. So I'm going to have to go back to my list of numbers. Now the 2 is already out, so it can't be a 2 the next time, but it could be the negative 2. But I already know where to go look for some more solutions. If I back up, negative 3 is a root, right? So that's my other real root that we saw on the graph. And so now I'm going to synthetically divide by the negative 3, but only on this part, because he's already linear. Once you're linear, you're good to go. He can just stay. So I'm going to take this purple part, and I'm going to synthetically divide the purple part by a negative 3. So purple comes over here, 1, 1, 1. Oh, it's a 3. And a 3, and I'm going to synthetically divide. Drop the 1. 1 times a negative 3 is a negative 3. Add, and I get a 0, and then I multiply, and I get a 0, and I add down, and I get a 1, and I get a negative 3, and 0. Yay. So now my purple part is this. Well, if x minus 3 is a solution, then x plus 3 is a factor, times this quotient down here. I'll give it a little bit more space. Here's my remainder. This is my constant. This is my x term. I don't have any of those. And this is my x squared. So I'm going to take the purple piece out, but everybody else comes along for the ride. And the purple piece is going to come out, and what's going to go in instead is x plus 3 times x squared plus 1. Now I can solve this. I can set each piece equal to 0, and I can solve. We already know the first part, that's x equals 2. We already know this part. This is x equals a negative 3. And I can see those on the graph pretty easily. Here are where my other two solutions are hiding. Now, real solutions can come in any multiplicity. So they could be only one of them, it could be 2 of them, it could be 5 of them, right? That's totally fine. But non-real solutions or irrational solutions like x squared plus 1, when I add or subtract the 1 to the other side, when I take the square root, I'm going to get a positive and negative square root of a negative 1, also known as I. Imaginary roots and irrational roots will always come in what's called conjugate pairs, and this is the complex root and the irrational root theorem. It happens like that because of the quadratic formula. Remember, the quadratic formula was a negative b plus or minus the square root of b squared minus 4ac all over 2a. Don't really care about that right now. What we care about is this part right here, that plus minus this crazy square root of the discriminant. That's what generates the problems. So remember, if you couldn't factor, you had to use that. And if you couldn't factor, that meant in all likelihood that it was going to be irrational, assuming it was something truly that could not be factored and you just weren't sure how to approach it, that it was either irrational or imaginary. And that's why they have to come in conjugate pairs, the positive and the negative version. So my other two solutions to this set, I got the 2 and the negative 3, would be an I and a negative I. You're not going to see the imaginary ones on the graph. You will see irrational ones. You just won't be able to get a nice number, but you will be able to use second calc, intersect, or 0 to find out where those are. But it will not find the imaginary ones for you. And you can kind of see them, right? Here's the, if you think about a negative 1, an imaginary plane would be right about here. So it would be these guys, right? If I come like through this area in there. So it's a little strange. They do have a purpose, just not one that we're really going to talk about all that much. But now you know how to find them. And you know how to verify. Because if I only would have found negative I, positive I, and negative 3, I would have had to go in and look for one more real. Because you can't have 2 real and 1 imaginary. But you can have 2 imaginary and then only 1 real. But I knew I had to have 4 because of the leading coefficient rule in that leading term. And so that's your worst case scenario of having to solve a polynomial.